Hello, everyone. We're just giving a couple moments here for everyone to join us. All right, thank you to all those who are joining us this evening. If you're here in California, or in the morning, if you're joining us from Thailand or elsewhere in Asia. Welcome to the second webinar in this two-part webinar series that we've organized in cooperation with Geohazards International to discuss observations from the 7.7 earthquake that struck Myanmar earlier this year. And this session will focus on impacts in Thailand and engineering observations. Before we get started, I just want to take a brief moment to introduce you to EERI if you're not familiar with us. EERI is the leading nonprofit organization bringing together professionals and researchers from a wide range of backgrounds and disciplines, both in the US and around the world, who are working on the common goal of understanding earthquake risk and advancing earthquake resilience in our communities. So if you want to find out more, I encourage you to visit our website and to become a member. I'll share a link in the chat a little bit later. I'm Elizabeth Angel. I'm EERI's Communications and Program Manager. I also want to acknowledge that support for this webinar series comes from the Federal Emergency Management Agency and from the Learning from Earthquakes Endowment Fund, as well as from the support of our members, including our subscribing members, particularly Computers and Structures, Inc., our visionary sponsor. So on that, I want to turn it over to Professor Eduardo Miranda, who's the co-chair of EERI's Learning from Earthquakes program. This is our flagship reconnaissance program. You can learn more at learningfromearthquakes.org. He will both be moderating our session and will be one of the presenters today.
Thank you, Elizabeth. So welcome everyone to this second part of our webinar series on this Myanmar earthquake. Very important earthquake with important and interesting observations, but also a lot of opportunities to learn from it all over the world. Today, we're fortunate to have two of the top earthquake engineers in Thailand to share the impacts of the earthquake over there. The first speaker is Professor Teraphan Ornthammarath, who's an associate professor of civil engineering at Mahidol University. He obtained his PhD degree from the Rose School in Italy. I had the opportunity to teach him dynamics, and we met back then. And he's now being a faculty member at Mahidol for about 13 years now. Our second speaker today will be Professor Pennung Warnitchai, who's a professor of structural engineering at AIT, the Asian Institute of Technology. He's probably well known to many of you. He's probably the top earthquake engineering in the country. He has been made lots of contributions over the years on a wide range of topics, and we're very fortunate to have him with us this morning. So with that, I leave it to you, Teraphan. Go ahead.
Okay, thank you. I would like to share my screen now. Can everybody see my screen?
Yes, looks great.
Okay. Good morning, good afternoon, and good evening from Bangkok, everybody. Today, I would like to talk about the far-field ground motion characteristic in Bangkok Basin during the magnitude 7.7 28 March 2025 earthquake. So this is the Bangkok skyline in April 2025. This is the places that we were very busy after the earthquake. We just inspect a lot of building after the earthquake. So this is the view that we usually see after the earthquake. And now I'm going to talk to you about the history of the Bangkok and seismic hazard, and then the observed ground motion in the Bangkok Basin. And then we're going to compare with the seismic design code. So as you know that in this year in 2025, the earthquake that start in Mandalay and propagate downward to Naypyidaw. The rupture length is quite long, 450 kilometers. And in this map, you can see that in the past 100 years, there are a lot of magnitude 7 occur in Myanmar, but none of them occur in this. So this is the seismic gap that we all have been waiting for. And it actually happened in March 2025. Luckily, in Myanmar, we have about 4 stations that could be able to record this earthquake. And in Thailand also, currently we operate about 23 stations that could be able to record this earthquake also. And 5 of them located in Bangkok. That you've seen a lot of video of the building vibration. So we're going to discuss about the observation in Thailand and also in Bangkok in this talk. So before that, I would like to go back a little bit to the history. This is the 1930 Bangkok earthquake that was felt intensely in Bangkok. And if I go back one slide, so this one is the 1930, that is the Bangkok earthquake, and it was really close to Bangkok compared to the 2025. And this is the description that the people feel, and then there was some few minor crack in 6 and 7-story building at that time, 95 years ago. The earthquake caused considerable alarm and people ran from their house into the street. During that time, we don't have the tall building and people still can feel this kind of shaking. So if you compare to MMI, it should be about 5. And some observation also something like unbraked stationary motor car was seen moving. So it more or less the same like what we observed in March 2025 also. So it means that this kind of earthquake happened in the past and we observed it before. So it is not unusual that we can see it again. And in order to explain that, we need to understand the basin. And then this is the picture that shows the topsoil in Bangkok. And later on, I'm going to show you some video that we have been compiled. And the first location is Sukhothai, that is located in the central part of Bangkok. And this is the video that we observed. So this is sloshing of the water in the river. Due to the soft soil, and even though it's quite far away already, we still can observe this sloshing. Another video is from Bangkok. This is the vibration of the tall building due to the soft soil. So even though we away from the seismic source, but due to the soft soil, these effects still can be able to seen at about 365 kilometers and 650 kilometers distance. Question then, in the past, did we observe this kind of shaking? We do feel the people in high-rise building in Bangkok, they do feel this kind of vibration, but not like the 2025. This is the picture of the people running down from the tall building. Mostly the magnitude 6.5 allow Myanmar, Northern Thailand, Laos, or Andaman. That would cause shaking on the tall building, and people would not feel comfortable, so they run down on the street of the Bangkok. But the scale of the vibration is not that large, but there's still a concern, so they're running down from the street. And this is the observation, like during that time, this is the record ground motion in Bangkok. The top two is the acceleration from the surface and borehole of one station in Bangkok from 2008 Wenchuan earthquake, that is in China. And these two are the stations that locate outside the basin. So you can see that on the same scale, you can see that the amplitude of the ground motion is quite large compared to the one outside the basin. So the effect of the basin is real, that you can observe like 3 or 4 times at least amplification compared to the station outside the Bangkok. And we have been expect this kind of event for some time. And we always said to the people that there is seismic gap inside Myanmar that we should be prepared for, and engineers should design for this kind of earthquake. So coming back to the global context, like global seismic hazard map, even though Thailand, like in northern western Thailand, the seismicity is not that high, but we call it moderate seismic region for the 75-year intermediate is about 0.2 to 0.3 G on the log side for the PGA. But for the Bangkok, it's located away from the no active fault. So the PGA at 475-year intermediate is lower, about 0.03 G on the log side. But this one is still not covered for the soft soil. So the value seems to be quite low. In the National Seismic Hazard Model, we're using two models, the left and then the right. The left is smooth seismicity with the active fault. On the right is the active seismic zone. And then we classify different kind of earthquake inside and outside the country, and also consider the active fault, as you can see on the left map. And on the red one is the sky fault that have the high slip rate. And we already consider also in our seismic hazard model for Thailand also. And also the subduction zone here that have been quiet for some time. For people that do not know about the seismic design code in Thailand, Dr. Pennung leading the development of the seismic design code. We using the model of ASCE 705. It first issued in 2009, and the latest one that have been updated is in 2018. It used throughout the country. The required value is the SA for 0.2 and 1 sec for 2% probability of accident in 50 years. So this one is we follow the ASCE as the standard. For the Bangkok itself, like I said, in the Bangkok, we have a lot of soft soil and the basin. So, so this is the Bangkok Basin Seismic Design Spectrum. You can see that it's quite unusual in the sense that normally you're going to see it, the high plateau at about 0.2 to 0.5 sec, right? But for the Bangkok seismic design spectrum, because the basin amplification, the peak is go about 1 sec. So Bangkok is about zone 5. So it's about here, this line. So it's quite unusual for the normal seismic design spectrum that the top one is go until 1 sec and then slowly going down here. So because of the Bangkok is away from the active fault, but we do have the soft soil. So the amplification going to be at the long structural period. And this is the seismic station in Bangkok. Here fortunately we have a lot of seismic stations that could be able to record this event, but some stations unfortunately cannot be able to record, but we still got a lot, like 5 stations out of this. And for this map show the water level from the ground. So you can see that the central part of Bangkok is quite low. because of a lot of the topsoil is located here. So this is the first one that we do after we got the strong motion record from EERI station in Bangkok. So this is the comparison between observed PGA with Boer et al. 2014 and Chow and Young 2014. The black line showing the steep soil and the red line show the soft soil. And for the dot in Bangkok, it is in the square, red square here. So you can see that mostly the ground motion prediction equation for the NGOS2, it underestimate this event. Like we can see that it quite go above the 1% high of the GMPE that we usually use in the active region. But if you compare this, the black one here is the station just outside the basin, and you can see that the amplification for the Bangkok subsoil for the PGA is about 3 to 4 times compared to the one outside the basin. So we still trying to figure out what is the reason for the observation for the strong ground motion in Thailand, that why is always larger than the 1% high. Well, maybe one of the things that we need to check further is there any directivity effect because the rupture moving from Mandalay to Naypyidaw, and whether we can see this in this strong motion or not. So this is for the PTA. So this one is for the SA at 1 sec. So you can see that the trend is still the same, that the observation is still larger than the ground motion prediction equation, both of them, both Boer et al. And Chow and Young 2014. And for the Bangkok, it's also quite larger compared to the one outside the basin, still the same, in about 4 times also. But for this time, for 1 sec, we still see that large variability compared to the PGA. Another one is we compare it for 6 sec. Well, we're going to come back later and compare the 6 sec. But you can see that, again, both equations still underestimate the current observation in Thailand, and especially in Bangkok. You can see that for Bangkok now, it's almost 5 or 6 times compared to the one outside the basin. So this is about the thing that we need to investigate more. What happened? Why there have been a lot of amplification in Bangkok? Well, when you see the previous figure that I just showing you, you might asking whether Thailand should using the NGOS too. In the past, like in 2014, we have moderate earthquake in northern Thailand, and then we also do the same comparison, but we did not see much underestimation of the GMPE compared to the 2025 earthquake. So this is the comparison for Boer et al. 2014 for the PGA and SA at 1 sec. So it's still quite okay for this equation for that event. But for the 2025 event, the event seemed to be produce larger energy compared to the normal one. So this is the question that we still need to try to figure out more what happened for this event in 2025. So this is the zoom up for the location in Bangkok and station outside the basin. So station inside the Bangkok is here. We have about 5 stations, and this is the location of the station just outside the basin. The value that you see is the PGA. So you can see that the PGA in Bangkok is about 0.02 G. And it is still quite low, but if you compare to the station outside the basin, we see the amplification about 3 to 4 times. And we have been working with the Japanese team they have been using GMA intensity scale for long period ground motion, and 2 stations in Bangkok, in the central Bangkok, they said that it's in class 3. Class 3, they said it is the same intensity scale compared to the one they observed in Tokyo from 2011 Tohoku earthquake. So the people in central Bangkok would feel the same way the people in Tokyo feel from 2011 Tohoku earthquake. And this is the record from the acceleration in the central Bangkok. This is in the north-south direction. This is the acceleration velocity, and this is the significant duration. So because the station is located quite away from the earthquake, so you can see body wave and S wave quite clear. And you can see that when the S wave reaching this station, you can see the development, the evolve of the seismic wave. In the first part, you still can see that a lot of high frequency content. And after that, there's long period wave energy. And if you compare to the significant duration, this is about 50% of the total energy located here. This one, we observe the largest PGA and PGV in this zone. So a lot of long period energy content in when the surface wave already developed inside the basin. And the duration is about 100 to 300 sec. So about 200 sec, about 3 minutes. So this is the people on the ground in Bangkok, they would feel the shaking on that day. If you're going to compare to the people feel on the high-rise building, there would be more, maybe 5 minutes or 6 minutes. For the PGA, for this station, we got about 0.02 G. And for the PGV, it's about 10 centimeters per sec. And then after that, we do the spectrogram, like we try to see what is the energy evolving over time. So when you start to see the S wave, the highest energy concentration is about between 0.2 and 0.4 Hertz. That is about 2.5 and 5 sec, about here. But when the surface wave starting to develop, the long period energy now start to dominate. So this one is about 0.1 to 0.2 Hertz, or about 10 to 5 sec. That is about here. So this is the long period energy that about 50% of the significant duration that we observe in the north-south direction for this station. And if we do it the same for three axes, like north, south, east, west, and vertical, we can say that the long period energy just seen only in the horizontal direction. We did not see in the vertical direction. So the surface wave move quite large only in the horizontal direction. And this one, and also accounting for about 50% of the total energy that we observe in central Bangkok. And if we consider this movement, it might be the love wave, because the love wave is the one that dominates in the horizontal direction movement. But the later wave, they would have also the moving pattern in the vertical direction also. So that is the thing that we consider that it might happen in 2025. And if you want to compare between what we observe compared to the basin characteristic. So in our team, we have the people do the microsonation, and on the left here is the depth to the bedrock. So the location of the central Bangkok, this is located where we see the deepest part of the basin is about 800 to 900 meters. And then the other station located in different depth. And on the right, this is the cumulative velocity. We try to understand the energy releasing over different stations. And we seen that the station located in the deepest part or in the central Bangkok, it is the one that has the highest energy. And the orange one here is the one located at the edge of the basin. And it looked like it contains the least energy here. So this is what we try to understand from the strong motion that we observe from this event. And right, we compare to the seismic design spectrum. So this is the DBE and MCE, and this is the spectrum that I showed before for the Bangkok. And I show in different map because in different figure because you can see it here. Like this red and green is the station in the central Bangkok. The shape look almost the same. Because these two stations, the distance is not quite much, like maybe 3 kilometers. You can see the amplification about 3 sec here. But the other station like PTNA that is located at the edge of the basin, you can see the amplification at maybe about 2 sec. So I would say that what we see, there still might be still different between amplification between different stations inside the basin. And what we see quite clear here is a zigzag here that is still another 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 thing that have large amplification due to the surface wave. So from our ambient vibration measurement for the tall building in Bangkok, for the 2 to 4 sec, that is about 20 to 50 story building. That is, so if the building has been built properly according to the seismic design code since 2009, the value that we given for the design still should be okay. But for the building about 6 sec, that is very few, like maybe 80-story building. That would be the one that we need to thinking about the update of our code in the future. And this is for the 5% damping spectrum. For the high-rise building, we have another seismic design spectrum that is for 2.5% damping spectrum. And still the same, the DBE is still going for most of the tall building in Bangkok. You still observe the different application for different station, like 3 sec, you can see very clear in central Bangkok. But at the edge of basin, you see at 2 sec, which you cannot observe in the central Bangkok. So there's still a lot of work that need to be done in order to be able to characterize what is the physics behind different amplification in different stations. So for the conclusion, the seismic design code in Bangkok has incorporated large earthquake at the long distance. Bangkok station amplify both amplitude and duration compared to the station outside the basin. Most long period energy concentrate located when the surface wave alive, and high spectral acceleration could be observed at the low damping also. This might be a concern for the tall building. Station located in the deepest part of the Bangkok basin show long period amplification, which had been previously observed. We has been noticed this one for some time, and we trying to develop the new seismic design code to account for this one also. But still, there more work need to be thinking about what is about soil nonlinearity. Did we see the linearity of the soil amplification for 2025 event? Polarization, directivity, damping, scaling factor, surface rate. This is the thing that we need still to work on. And that would be all for me. Thank you.
Thank you very much. And now we're going to switch to Professor Warnitchai.
Okay, let me share my slide. Okay. Can you see the first page of my slide?
Yes, it's correct now.
Okay. Let me start my part. I'm going to focus more on the impact of this earthquake on tall buildings in Bangkok. As you can see in this slide, you can see a large number of tall buildings in Bangkok, the capital city of Thailand. We have more than 1,000 tall buildings, and many of them have been strongly shaken by the earthquake from Mandalay. Okay, let me start by showing this one. Oh, okay, but this one I'm going to skip because Teraphan already showed the seismic activity of this region and active tectonic source. So let me move to the third slide. This is about the Mandalay earthquake. The slide made from USGS showing that this large earthquake was created by a rupture along the sky fault, but it's a rupture over the section from Mandalay to Naypyidaw, and it's produced a very large earthquake, strong earthquake. And as you know, the ground shaking intensity is very high near to the rupture zone, the red zone. But as the distance from the rupture zone increase, the ground shaking intensity reduced with the increasing distance. This is normal. What is not normal is the effect of ground shaking becomes strong again in Bangkok. It's down here. I hope you can see the mouse. It's down here in Bangkok. It's about 1,000 kilometers from the epicenter of the earthquake. Now, the main factor that make the effect become strong is the presence of special geological condition in Bangkok. Okay, I think Teraphan already showed this slide, but it shows that Bangkok is in a red zone. The red zone here means the top layer soil is a soft soil, very soft soil with the VS30 or the average shear wave velocity over the top 30 meter is lower than 180 meter per second. So in the red zone is in fact a large soil basin with the top layer soil is a soft clay. Now, if we look at this picture, it will give more details about this red zone. It's in fact a large soil basin. The picture shows you the depth from the surface to the bedrock. The bedrock is defined as the layer with the VS shear wave velocity around 2 kilometers per second. So this is a map showing the depth to the bedrock. In Bangkok, the depth is around 800 meters. And the basin is quite large. From the east to the west is around 200 kilometers. From the south to the north is around 150 kilometers. Many provinces are located within this basin. And the capital city is just at the center of the basin. We actually spent many years, my research partners and myself have been spending many years study this basin. We use a technique called array microtremor measurement, which allow us to identify the shear wave velocity from the top layer down to the bedrock over more than 1 kilometer. So we have this result. We took the measurement more than 180 sites and come up with a model for the soil basin, which allow us to conduct to make a proper site response analysis. And the analysis show that the basin itself can amplify low frequency seismic shear wave significantly. Low frequency means long period. So the basin will produce long period ground motion on the top soil surface, which will give more impact to long period structures. Okay, I think this issue may be well known to earthquake engineers because it happened in many cities like Mexico City. So for the case of Bangkok, after we have the earthquake in Mandalay and a seismic wave arrived Bangkok, this is what happened. I hope you can see the video. Okay, this show you that the swimming pool on the top of many tall buildings, the water slosh and spill over from the top down to the ground. And the next slide is show a large different movement between the two towers, causing damage to the connecting grid. The next video shows the impact to our SkyTrain mass transit system, rocking of its train vehicle. The last slide shows the impact to the state auditor office building under construction, and it was completely destroyed by the impact from earthquake located 1,000 kilometers away. Okay, in order to explain this issue more clearly, I made this kind of animation showing 3 different buildings. The one on the left is a very tall building with about 50 stories, and the natural period of a fundamental vibration mode is about 5 seconds. The second one is about 25 stories with the natural period 2.4 seconds. The third one is about 10-story building with natural period about 1.1. Now, if the ground move is a long period ground motion with a period matching with the natural period of the tall one, it's going to produce stronger effect to the tall one by what we call resonance effect. Okay, the matching of the ground motion period with the natural period of the structure. But when the ground motion movement change to a 2.4 second period, matching with the middle one, you have a stronger impact, again by the resonance, but this time resonance with the middle structure. And then if the ground motion move at a shorter period, 1.1 second, is going to produce more impact, more effect to shorter period structure. For the case of Bangkok, we believe that we are somewhere close to the first case and second case, but not the third one, because the characteristic of the basin tends to amplify more in a long period range. Okay, I think that helps explaining what is happening in Bangkok. So when we combine our understanding about Bangkok basin, the way it's amplified the ground motion, with our probabilistic seismic hazard assessment, considering many tectonic sources around far from Bangkok or close to Bangkok, we arrive at a conclusion that Bangkok and surrounding province are at risk of disaster from distant large earthquake. We conduct a so-called seismic hazard de-aggregation analysis to identify what are the major earthquake scenario that could produce a large impact to Bangkok, and we obtain about 3 main scenarios. So first one is an earthquake of magnitude about 7 to 7.5 in crustal active fault in Kanchanaburi. The next one is earthquake of around magnitude 8 along the Sakai Fault in Myanmar. Well, the second case is more or less the case that we have 4 months ago. The third one is not happened yet, but it may happen sometime soon in the future. It's an earthquake of around 8.9 to 8.5 to 9 in the megatrust zone we call Arakan megatrust zone, subduction zone in the west of Myanmar. So all these three could produce a strong effect to Bangkok. Well, we made this slide many years before the earthquake on 28 March, and we actually explained to many people. And in fact, Bangkok and surrounding province has been preparing for such earthquake. We introduced so-called ministerial regulations require all tall buildings to be designed for seismic resistance. Okay, since 2007. So that is a regulation. And we also developed national standard for seismic resistant design of building and structure since 2009. And then it has been revised in 2018 and become effective in 2019. So the regulation and code, we have it since around 2007 to 2009. In the latest version of our standard, I forgot to tell you that our standard, we use ASC 7 as a model code. So I think if you are familiar with US standard, then you can easily understand our standard. For the Bangkok zone, we divide the whole basin, entire basin, into 10 different zones, micro zones. And Bangkok, the capital city, is in zone 5. Surrounding provinces are in other zones. For each different zone, we have design spectrum. This is similar to what you call DBE spectrum, design basis earthquake spectrum, which is set to be about 2/3 of the MCE spectrum, maximum considered earthquake spectrum. So this spectrum are made based on our seismic hazard assessment combined with our understanding about the soil basin. And as Teraphan explained to you, the spectrum is not like a normal design spectrum you can see in US code or in other country code, but it shows a rather high spectral acceleration in long period range. Okay, this is a ground motion record. Teraphan already showed this, but what I want to say that it's a long duration, low intensity in terms of acceleration, long period, because you can see the time scale in second. Long duration because it's shake more than 2 minutes. And the top one is north-south, the picture below is east-west. So this is a station. We have about 5 stations. And the first thing we did after we obtained this ground motion is to compare their response spectrum with our design basis earthquake spectrum and MCE spectrum. So the yellow one is the DBE spectrum. The violet color spectrum is MCE spectrum. The record ground motion shown here. So it's quite lower in relatively long, not so long period range, but in a long natural period range is comparable to DBE, and in longer period range is even closer to MCE or sometimes exceeding MCE. So this is a comparing between what just happened 4 months ago and our target spectrum that we use in the design. So based on this, we actually can expect that there might be some severe impact to our buildings, but we do not expect buildings to collapse if they follow properly our seismic design code and standard. So this is a kind of rough statistic of the damage made by, you can see, Thailand Structural Engineering Association. I just borrow that slide and show it to you here. They sent many volunteer engineers to check many tall buildings in Bangkok after the event. And they found that several hundreds of tall buildings have damage to their non-structural components like partition brick walls, ceiling, elevator system, and many others. So although it's not affecting the safety of the structure, it affects seriously the serviceability of these tall buildings. About 10 buildings, they have damage to the structural component, mostly to the reinforced concrete wall, or we call shear wall or core wall. And one building that you have just seen or collapsed is a SAO building. Okay, let me show you some idea about the picture of damage. This is what we call slight to moderate damage to non-structural masonry walls. You can see cracking, clearly visible cracking, plaster damage to this building. These are the non-structural wall, masonry wall. But some have more severe damage that you can see through the wall. Okay, of course, it's not easy to repair. You just have to demolish and make a new one. And in some buildings, around 10 of them, we found damage to the structural components. Like this one is a 25-story hospital building, and you can see the damage to reinforced concrete core wall. Concrete crush, reinforcement bar buckle. Okay, and when we take a close look, we saw bad seismic detailing. They have lap splice or vertical rebar. Okay, I think that lead to brittle form of damage for this building. Many buildings have a damage like this. And this is another one, damage to the shear wall. This is a 45-story building, and serious damage concentrated in floor level 9. It happened not just one side, but all around. So this building is very close to the collapsing, but it's still standing. And they are now trying to repair this building. Now, just to understand the big picture, understand the impact of this earthquake to tall buildings, we think that by looking at the spectral acceleration alone may not help, because the damage, many of damage may be associated with the deformation demand. So we are trying to calculate this parameter we call roof drift ratio, delta by H. Delta is the top displacement at the roof. H is the height of the building. We believe that roof drift ratio is a good index to relate it with the observed structural damage. Delta, we actually first calculate spectral displacement, but the spectral displacement is a displacement of a lump mass single degree of freedom system. So we convert that into top displacement of distributed mass first mode vibration of the tall building by some factor. So by doing so, we can compute roof drift ratio from available ground motion record in Bangkok. And this is the result. Okay. The vertical axis shows roof drift ratio. In this picture, 0.5% mean roof drift ratio about 0.005. And horizontal axis show the natural period. Okay. Before I go further, this picture are made from, on the right is the ground motion north-south component. On the left is east-west component. Okay, and there are many curves with different colors. So actually, different color is for different level of damping ratio. in tall buildings. So let me explain a little bit more about this. I think most of you know about damping ratio, but just to be sure, in the past, we used to believe that our building have damping ratio about 5%. But more recently, when we look at the code like tall building guidelines for design of tall building, like a TBI guideline and CTBUH, they recommend that to use lower value of damping ratio, like 2.5%. So we actually adopt that one in our recent code. But after the earthquake, a few days after the earthquake, I was contacted by Professor Miranda, and he pointed out this issue that the damping of tall building might be lower than 2.5. So we carry out some investigation. We collect the data from 4 buildings. 2 of them have acceleration sensor installed on the top. And the other 2, we have a movement record from video picture analyzed by a Japanese expert. So from the data of 4 tall buildings, we arrive at a conclusion that the damping of our buildings is likely to be much lower than 2.5%. It could be as low as 1%. So I have no time to show the result, but if we have time later in question, I can show more information about this. So under effect of long duration ground shaking, long period, the structure with a different damping ratio may have quite different level of response because it's a resonant type effect. So as you know, the resonance, the damping play a very important role. The building with low damping tends to have much higher response amplitude. So the response could be very sensitive to damping ratio. So let's come back to here. So you see several high roof drift ratio for different period range. But let me tell you that in Bangkok, the period of, for example, 3 seconds mean about 30 story, 5 mean about 50 story, 7 mean about 70 story, roughly. But in Bangkok, about, we have only 10 super tall building with a natural period somewhere between 6 to or higher. So very few number of tall buildings above 5 seconds. And we have around more than 1,000 buildings with a natural period between the range of 1 to 5 seconds. So most buildings are concentrated in the range of 1 to 5 seconds. And within this range, you can see the top peak of roof drift ratio happen in the range of around 3 seconds. Okay. The blue curve are for low damping 1%. The red and orange is for 2.5%. The green for 5% damping. But our tall buildings are likely to have damping somewhere between 1 to 2.5%. So they are on the high side in this plot. And you can see that strong one may happen around 3 seconds. Okay. And from the data we have, the building with having structural damage are mostly majority of them have the natural period around 3 seconds. I put further some color band, yellow and orange color. Yellow is for level of story drift. We approximate roof drift as an average story drift. The yellow zone is for slight to moderate damage to non-structural wall. And the orange zone is for the level of roof drift that we can expect severe damage to non-structural wall. So we have not yet checked this with the real statistic of damage data yet, but that will be the next thing we will check. Okay, I'm going to skip this, but this one shows the SAO building. And from our modeling analysis, it shows that the building have a natural period close to 3 seconds. I think that's one of the reasons why it was damaged, because it's very high site deformation demand. Now come back to this one. This is for the picture I showed you earlier, but it's derived from one station. If you look, next time, if we want to prepare our structure for the future earthquake, we may have to make sure that our building should be able to handle this level of deformation demand, or maybe higher, because this is not the highest earthquake we anticipate. It could be stronger. So we should be able to handle the roof lift ratio larger than this. Now let's look at the typical structure we have in Bangkok, Thailand. These are typical. The tall buildings are basically made from reinforced concrete slab column frame that designed to carry mainly gravity load. And we have reinforced concrete wall and core wall to resist lateral load, which are wind load and seismic load. We use a lot of masonry infill wall, non-structural wall, and our buildings have typical irregular feature: vertical irregularity, torsional irregularity, plan irregularity. So this is a typical structure. This structure for slab column frame, we believe they are quite deformable. For the least level of roof drift ratio below 1%, there should not be significant damage to the slab column frame. But we cannot say the same thing for the shear wall, because the shear wall, we found many brittle form of failure, lap spike failure, and we believe some of them have shear failure. So RC wall are quite capable of having brittle failure mechanism. So if we put more emphasis on trying to eliminate this brittle failure mode, we may be able to make our shear wall more ductile. And if we can eliminate all possible brittle failure mode, our entire structure should be quite deformable, maybe up to 2% roof drift ratio. This shows you an idea of our analysis, assuming that the shear wall is ductile, and we perform cyclic pushover. It can maybe deform up to 2% roof drift ratio, or even larger than that. Okay. Now, if we come back to see this, if we have our frame system combined with the ductile shear wall, I don't think we should worry much about this level of roof drift ratio. But the point is, I think this is not an issue that we emphasize in our standard. This is maybe the issue we need to focus more in the future to improve our design, to ensure the safety of our tall buildings. Okay, but having ductile core wall in our system may not be able to prevent the non-structural failure. I think if we want to suppress non-structural failure, we also, I think it's shown clearly in this picture that we need to increase the damping. Okay, if we increase the damping, then the roof deformation demand will significantly reduce, because the response is resonant type. This one shows the roof drift ratio using other ground motion record. This is in the central Bangkok. You can see the peak at 3 seconds again in the north-south direction, but in the east-west, the peak happened at 4 and 5 seconds. So there's a variation in the ground motion characteristic in Bangkok. This is another station showing 3 seconds and again 3 seconds, this one. Okay, To increase the damping, we may need to install damper inside the buildings. Well, of course, there are many kinds. Viscous damper, like shown in this picture, or oil dampers, or viscoelastic damper, or metallic dampers. But in Bangkok, we have not yet tried all this issue yet, because this may be the new issue for Thailand. Okay, and this is by this earthquake, then we realize that we have a damping problem. Our buildings have damping much lower than we anticipate. And to improve the performance, then increasing damping might be a good solution. I think that's the end of my talk. I'm willing to answer any question the floor may have. Thank you very much for your kind attention.
Thank you very much, Professor Warnitchai. That was a great talk. Now I will just wrap, adding a few short comments, perhaps a little bit with U.S. perspective. And as this earthquake illustrates what I would say, how earthquakes sometimes play trick to us. And I just want to highlight a few remarks. First, the length of the rupture, which, as you heard, is 480 kilometers. That's the distance from San Jose to downtown Los Angeles. If you were to take a flight, that would take about 45 minutes to get there. But this earthquake ruptured that length in about 80 seconds. And in terms of the distances, as you heard, that epicentral distance to Mandalay was about 1,000 kilometers from Bangkok. That's the distance from San Francisco to Seattle. And even if you take the shortest distance to the rupture, that would still be 650 kilometers, which is the distance from San Francisco to Irvine. So we're talking about very long distances that typically we would not be concerned about. Prior to this earthquake, the only other earthquake that I'm aware of that had produced collapses at very long distances was the 1985 Mexico earthquake, where there were collapses that occurred about 450 kilometers away from Mexico City. And this is just one of the collapses that occur there, and some of you may remember. The other aspect that is very important to keep in mind, and this is why our guest for many, many years warned about the issue with long magnitude earthquakes, was that in addition to being very large, they have a very different frequency content to that of small and moderate magnitudes. And if we were to put this, and we take the ratio and how these amplitudes of ground motion intensities increase with increasing magnitudes, what engineering seismologists call the magnitude scaling, it's very different at short periods that affect low-rise buildings than what happens at low frequencies, long periods that affect high-rise buildings. So it's very, very important. But even when our guest had basically foreseen that this was going to be a problem, we saw that it was still not enough, and there were big surprises. They were well aware, and the top experts on the site conditions on the Bangkok basin, and still, as you heard, even the most advanced ground motion models for crustal earthquakes underestimating the PGAs at Bangkok by more than a factor of 10. And these are some older studies that were done in collaboration of Thailand with some US researchers, Scott Ashford, that many of you may know. And they published a number of papers where they were warning about these amplifications that it could occur because of the soft soil. But as you heard, most of this was related to the top 12, 18 meters with shear wave velocities lower than 100 meters per second that produced these large amplifications, say around 1 and 2 seconds, that were incorporated in the recent revisions of the building code, but did not foresee these very large amplifications. It's just a very recent paper by our speakers that was published just 2 years ago, where they looked at horizontal to vertical spectral ratios using a number of ground motions, and in those they were able to see and see that there could be this very large amplifications at long periods, such as 5 or 6 seconds. And as I'm pointing there with those two arrows, they're particularly large, these amplifications, for the earthquakes that are larger than or equal to 7.5. And this is basically one of the main reasons of what our speaker is just pointing out, this unusual but very large amplifications at very long periods that exceeded the ones in the code, even the ones in the MCE, as you see in this image. This issue of the damping that was mentioned is very important. As you know, damping in buildings tends to decrease as the building becomes more slender, taller. And in particular, for buildings taller than 100 meters, they can have damping ratios that are lower than 2.5. This was incorporated in performance-based regulations here in California for the service level earthquake, but not for the MCE. And this might need to be revised, and we really need to study this careful, because this displacements and intensities that we saw, as we saw, they exceeded the MC level. And as we also heard, there are many buildings, tall buildings. Here I'm just showing a few of them, but there are 39 buildings in Bangkok with heights taller than 200 meters, and 190 buildings with heights of more than 150 meters. And I added there, just for comparison, what happens in Los Angeles, where there are only 13 taller than 200 and only 30 taller than 150. So the danger posed in Bangkok, it's much larger than what we have here in the United States, in Los Angeles, where we also have this deep deposits. The other thing, just to highlight, it's not only that the damping, it's very low in these tall buildings, but that we continue to learn about the effects of damping. For example, this is a record from the Chichi earthquake that I'm using here to illustrate that the effect of damping is very different in spectral peaks than in spectral valleys, where the effect of damping may be significantly smaller. But when we use damping modification factors, we average these peaks and valleys, and we may underestimate what happens at spectral peaks. This is one of the damping modification factors, probably one of the best that we have, that was developed here in California at UC Berkeley. And you can see there that for 2.5% damp, we would expect 20% larger actions, but then for 1% damp, larger, but at very long periods, these amplifications would go down. But whereas if you now were to look now what happens at very soft soils, and this is one example from a station here in the Bay Area in Foster City, where you see very large peaks at the 3 modal periods of the soil deposits, where the effect of damping is much larger than you have in the spectral valleys. And these are examples from the ground motions that we just heard about that they kindly shared with me, and I'm just showing you 2 of the components of these records. And you can see there with the red arrows that the effect of damping is much larger in some periods than in others. And I'm not aware of any building code anywhere in the world that takes this into account. And it's just very recently that we developed here at Stanford some models that account for these differences in the effect of damping at structures built on soft soil. And with that, I just want to say that this earthquake, like many others, provides an opportunity to continue learning from earthquakes, but that this learning must not stay in papers, reports, or webinars, but it needs to be incorporated to update our building codes and in engineering practice in order to translate this learning to actual risk reduction. And with that, I want to wrap up, and we'll move to the Q&A. So if you have not done it, in the Q&A, you can type your questions. There are already some questions, so I'm going to go ahead and read some. There's a first question that asks, if you have considered basing edge effects that could cause multiple amplifications in Bangkok.
Still not quite clear. Can you repeat the question?
Yeah, if in addition to the amplifications, if you have considered further amplifications of the surface waves as they touch the edge of the basing and they basically get trapped inside the basing.
Oh, I may first try to answer this, and Teraphan may add. The model we use is a simple 1D vertical shear wave propagation analysis. So it's consider only the effect of shear wave amplification. The model we have does not take into account of surface wave amplification. But from the data we have from this case, it's become quite clear that we may have a significant portion of surface wave. So it's become quite clear that we need to upgrade our basin model to account for surface wave effect and surface wave amplification by the large basin. Yes, I think that's the answer.
Thank you. Yeah, and here one thing to keep in mind is that sometimes this in more narrow basins, these surface waves get trapped and they basically bounce against hills or foothills. But in this case, as Professor Warnitchai mentioned, the width of the basin in the east-west direction, it's 250 kilometers. So,
yeah.
There might be
very large
basin
this compared to the depth. It is very large basin. Horizontal dimensions are very large compared to the depth. That's why we initially thought that the effect of 3D may not be so significant, but it's quite clear that our normal side response analysis cannot account for any surface wave, but not bouncing between the boundary, but it's the model that should account for effect that amplifies surface wave propagate from a source.
Thank you very much. There's another question that asks if there has been any effects or damage on long span bridges that also have long periods.
Well, not much damage to elevated highway, but they have some significant damage to some cable stay bridge that we have. I did not include that into the presentation, but at least two of them, I heard about the damage to the damper inside and also to the connection between the main girder and the pylon. They have some pounding effect. So these are a few long period structure that are not building type. Yeah, also affected by this long period ground motion.
There's a third question that asks, you showed a building that had concentrated damage to the shear walls at the 9th floor, and the attendee asked if there's any explanation as to why it concentrated at that level.
Well, one of my research partners are taking care of this. I have no detail yet, but I also asked the same question to him. But he told me that there's no vertical irregularity above or below that level. It might be due to some quality of construction of shear wall over there. That's his guess. But okay. I think we may be able to tell more if you ask the question maybe a year later.
Yeah. You mentioned something about the collapse building that it had a period probably very close to that 3 seconds that shows up in several of the ground motions. But one of the attendees asked if there's some preliminary explanations for that collapse.
Well, collapse, we have a comprehensive investigation conducted right after the collapse. So the investigation was led by the Department of Public Works and Town Planning. But I was instructed not to inform anyone because it's under police investigation. who is right, who is wrong. But I think what I can tell is we actually carry out the detailed nonlinear seismic response analysis of as-built structure, and we found that it's quite likely that the building failed by shear failure at the base of the core wall. Okay, we have a video analysis showing that the collapse triggered by the vertical settlement of the core wall. And the reason for having vertical settlement, rapid settlement of the core wall is because the lower zone part, the shear demand may exceed the shear capacity of the core wall. I think that's all I can tell now. The others, probably I may not be allowed to explain.
Mm-hmm. There's a question related to non-structural components that you show damage to different types of finishes and infill walls, and the attendee asked, what would happen if the so-called non-structural walls are isolated from the deformation of the structural framing?
Oh, well, our practice is to make the wall connected to the bounding frame. And if we are going to change this practice, may be quite difficult. We have to prepare many things, and it will be more expensive to do so. But of course, if you can do that, then there will be less damage to the non-structural wall. If you can isolate them by still making them stable out plane. Yeah, if you can do that. But it's not our practice now. The practice is to make it connected directly to the bounding frame.
Yeah, if I may add, I'm aware of several details that have been proposed in recent years to do that, but very few buildings have incorporated that. But it would be something to do more research, as Professor Warnitchai just mentioned, could reduce significant the damage to this type of components. There's another question related to the distance. Mentions, I understand that the large distance in this earthquake it's a major cause of damage to tall buildings because of the long period to the large depths of this deposits. And that you talked about the low damping in these tall buildings, but it asked if you consider the low damping effect during the design of the tall buildings in Bangkok.
As I mentioned earlier, in the past, we assume the damping of tall buildings to be about 5%. But more recent version of our standard, we bring it down to 2.5%. And we ask engineers to look at design spectrum for 2.5% damping. When they look at that, then they calculate the estimate the force in the building based on design basis earthquake spectrum of 2.5%. Now, with the new data, as pointed out by Professor Miranda, we may have to consider even lower damping, but that for the future. I think we have to learn from this earthquake and have more evidence to convince everyone that our structure have effectively lower damping than we used to believe. This is not easy because when we bring it down from 5% to 2.5%, we got many negative feedback from engineering communities. We are kind of changing the practice. So when we bring it down, there's increasing the force demand and many other things. So a lot of complaint from engineers.
Yep. There's one comment that congratulates the speakers. They have done a great job, and comments that perhaps we can consider the resonance of the basin to explain some of these amplifications in the long period. This comes from Professor Sanchez Esma. from UNAM in Mexico City, who's an expert on this basing effects. There's one question related to the practice in Thailand, and ask if it's different, if it's similar to the US in the sense that the design basis earthquake, the elastic spectra would be reduced by reduction factors for design of its shear walls.
Oh,
Yes.
okay. Yeah, Teraphan want to say? Yeah, please
No,
go ahead.
I just want to say that yes, we do the same practice like the US engineer. We're taking the reduction factor when we design the shear wall.
Yeah, but I want to add that, for tall buildings, is a structure which have many vibration modes, and the impact, the effect it's not just produced by fundamental vibration mode, but it also have a contribution from higher vibration modes. So engineers in Thailand in the past, we use what we call response spectrum analysis, the procedure in ASC7. But later on, we found that RSA divided by big factor R may underestimate the shear load in the tall buildings. So we modify the response spectrum procedure. We develop a so-called modified response spectrum analysis. We just divided only the first mode shear by R, and we multiply it by omega factor. And the shear contribute from higher mode we consider as the elastic shear. So this one give a shear load closer to the shear demand computed by nonlinear time history analysis. So we have our own procedure to estimate the shear and higher mode effects for tall buildings. Yeah, I think this answered the question. We do not follow everything. We take some part from US model code, and some part we modify, like a spectrum. We make it match with the local condition, and the analysis procedure we also adjust to somewhat we think is right, and put into our standard. Yeah.
Thank you. There's another question related to damping, that using a 1% damping makes a lot of sense for some of these tall buildings that are behaving linearly elastic, but ask if, in your opinion, this would also apply to structures that may go in the nonlinear range.
I think the damping we are talking about is a kind of equivalent inherent damping for large elastic response. When the structure go into highly nonlinear, there will be additional damping from hysteretic loop and response and other damage in the structural component. Then we have automatically increasing in damping, and I think that will account for additional energy dissipation. But for the case of Bangkok, we need more accurate damping in large elastic range, because tall buildings in our case, I think the response is still in approximately elastic. You see, as you see in my presentation, is the roof drift ratio is lower than 1%. We normally found that the core wall will begin to have flexural yielding at the roof drift ratio around 1% or plus minus. Okay, so the roof drift ratio below 1%, the structure is still essentially elastic with slightly nonlinear effect. So I think that in that range, inherent damping play a very crucial role in controlling the seismic demand in the building. So the issue raised by Professor Miranda, I think, is very important. What is a true damping in a tall building is a critical question we have now.
So we have several other questions. Unfortunately, we've run out of time. I'm just going to read two more. One from Professor Rihal asked to Professor Warnitchai, can you please comment on the performance of facades and cladding?
Oh, well, in Thailand, our buildings are reinforced concrete building, and we actually, it's our practice to use a lot of masonry partition walls for exterior wall, for facade, for interior partition. And more recently, we have precast system, precast concrete panels as the exterior. Yeah. And most of the time, the design of this just make a partition wall locked to the bounding frame, make a precast wall connect rigidly to the structure. I think after this earthquake, I think people are going to pay more attention to make it more flexible, more deformable. Otherwise, these non-structural components are going to be the first thing that will be damaged by the building sway.
Yeah. So I'll read the final one. It's a comment that might have been triggered by a comment that I made in reference to Los Angeles. And the attendee comments that the depth in Los Angeles it's larger, but the how soft the deposits are not so soft and of course in Bangkok they're even much softer than let's say in La Cienega in Los Angeles. So he asked if you know of other basins with similar soft soil conditions as what you have in Bangkok.
Well, the fact that the basin amplify the ground motion is not only because of the top layer soft clay. Soft clay just play one role, but it's the entire basin with a depth of around 800 meters that amplify long period ground motion. It's not just the soft top layer. We used to focus more on the top layer, but now we understand that it's the entire basin, that the entire depth of the soil basin that amplify the ground motion. We actually, after we study the Bangkok basin, then we move our team to other basin, like in Chiang Mai, the northern Thailand, Chiang Rai in the northern Thailand. We also found that they have a different basin property, amplify different range of period. And in the latest earthquake, the Mandalay earthquake, we also have a record in Chiang Mai basin, and it also show long period movement, long period motion, up to about 4 to 5 seconds in Chiang Mai basin. So that's another story. We are going to study more, because it's not just limited to Bangkok. It's also happened to other basins in Thailand.
Thank you very much. So with that, I want to thank everyone for your participation. I hope you all enjoy this webinar as much as I did, and I'll pass it on to Elizabeth.
Great. Thank you so much to all three of our speakers for sharing those insights with our audience. And thank you to all of those of you who attended today. Just a few brief points at the end. I wanted to let you know that a survey will pop up in your Zoom window after the webinar closes, and you'll also receive a link to that by email tomorrow. We really appreciate you giving us feedback that helps us improve our webinar offerings. You can learn more about EERI at our website, and we encourage you to become a member if you're not one. And you can also donate to the Learning from Earthquakes Endowment to support EERI reconnaissance and response work after earthquakes. And then finally, once again, I just want to acknowledge the funding from FEMA, from the LFE Endowment, and from many EERI members that makes these events possible. So thank you for joining us, and we hope to see you again at future webinars. And I'll just add there briefly, we will have our Northern California regional chapter has an additional quick quake briefing on the Myanmar earthquake coming up later this month. So stay tuned, check out the Pulse newsletter, or look on our website under upcoming events if you want to register to join that. All right, thank you everyone. Good night or good morning.
Bye.
Bye.